Okay, let's start now. Trinani said he won't join our class, and the second thing is the discovery cluster has resolved our partition problem. So now everyone is free to access to the our own reservation. No, not partition. The reservation we have. Also, yeah, that's it. So today is our last lecture for the GPU programming class. So today we will go over these three topics. It's about transferring between the host and device transfer memory, um, also concurrency and dynamic parallelism. So besides the fact that we would like to increase the speed of kernel execution, we also need to minimize the amount of time it takes to transfer the data. And there's one thing you must keep in mind: the bandwidth between the host and the device is much lower than the device-to-device bandwidth. So the purpose of, I mean, the objective we have now is to uh, increase the speed, increase the bandwidth, about how to uh, increase the bandwidth, lower the time you spend when transferring your data from host to device or device to host. There are a couple ways we can do. Actually, there are four ways. Uh, the first one is you can, let's see, reduce the amount of data you have to transfer. You can do some compression method, compress your data from the host. So like if you have a sparse matrix, there must be a lot of zero. You don't want to transfer those zero. You can use some C coordinate compression method to reduce the data. Also, you even so if you reduce the amount of data transferred to the GPU, you might do some execution on the CPU side. So it is not always good to transfer a large amount of data and execute on the GPU. That case may not be the most optimized case. You need to think about that. And the second is the achieve the highest memory bandwidth between host and device. That is what we will talk about later, the pinned memory or the page locked memory. Um, the third thing you can think of is instead of doing many small transfers, just pack the small transfers into a large, just do the transfer once, so you will eliminate some overhead. So like if you need several data structures, you can first allocate all of them, so and then copy all the data once, maybe at the beginning of the program. The fourth way is to do the concurrency. So overlap the kernel execution with the data transformation, with the data transfers. Mm, yeah, that's what I said. We need to consider the cost of moving data across the PCIe bus. Uh, so this is the first topic, is pinned memory. Uh, So when on the left side is what we used to do. We first allocate our data on the host, which is the pageable memory. But this pageable memory could not be directly get copied to the device memory. So the GPU cannot access the data directly. So what the CUDA driver will do is allocate a temporal page locked block. Is this allocate another block of memory called the pinned memory and copy the host data to the pinned block. Then the driver will copy the data from host from pinned memory to device. So and delete the pinned block. So if we use the pinned memory method, we will see on the right figure, there's no pageable memory step. So we directly allocate our host memory as a pinned memory. So why there's a page block pageable memory and another is page lock block is in the DRAM, all the memory are split into multiple pages. So those pages can be swept into the disk. So like if the CUDA driver try to copy a segment of a data which is on the pageable memory. Before the driver can do that, it is not sure that segment of data is really located on the DRAM. So that's why the pageable memory should copy itself to another located pinned block. This pinned block won't move; it will stay on the memory. So in this case, if we directly allocate our host memory on the pinned memory on the page locked block, we make sure when the CUDA driver try to copy the host memory, host data, the data is guaranteed to be there. Let's see. How do we write code to achieve this goal? So instead of like this snip of code, this is the regular man copy you do. And in order to allocate the memory on the page locked block, you do CUDA man copy host. It's just adding a host. Then so this is allocated to the pinned memory. Then you have to free that, use CUDA free host. So you might have problem on you couldn't be able to pin that memory. So that allocation may fail. So you'd better do the CUDA check. I think that is one function. You just check the return value of those function and see if it is successfully allocated. Yeah, you should not over allocate pinned memory. Those pinned memory is directly reside on the physical memory. So if everyone just just allocate the pin memory, the operating system will run out of memory. So that part is not managed by the operating system. But operating system has multiple things to do. Yeah, that's the pin. Yeah. Is any question related to pinned memory? If not, I will continue talk about unified memory. So previously, we have two separate memories. One on the CPU side, one is on the GPU side, and they are separated. But we know we have the data which is used from GPU side, but maybe the data resides on the CPU side. How do we use the data that is not located on the GPU? We manually copy that. So that means we manage the memory by ourselves. But when you use the unified memory, the runtime will manage this memory copy by itself instead of you do that. It is very convenient. So when you think about unified memory, you do not need to consider the underlying memory management. So you view only one memory space. So here is called there's a pool. So unified memory creates a pool of managed memory, so that is shared. So this memory accessible to both CPU and GPU. So just using a single pointer, you don't need to care where this pointer point, where the data this pointer point to is located. The system will automatically migrate the data. So if you program your code well, you don't need to think about it. But if you are in a hurry, so you want to, I mean, in that case, you are using a unified memory. You try to access to a array, but you don't know where it is located, but you can directly use it. The unified memory will responsible for if that data is located on the CPU, it will copy the data to the GPU. But if it is already in the GPU, you can just access it. So why do we do that? Is you can, so in this case, the code you are writing is very similar to the CPU code. So the reason why we use unified memory is it's easier to program. The simplicity, just one pointer used by the host and the device. Oh, another thing is using unified memory can potentially take more advantage of the data locality. So the data migration happens on demand. So that means it only brings the data that is needed. So the unified memory manage those copy. So maybe if you as a programmer may bring a large amount of memory which is not fully used. But if we, as we learn more features about the CUDA programming model, you will see have the ability to management the memory by yourself is maybe a better way uh, to get to increase the performance to tune your program. So like here, doesn't use will perform better. Yeah, it add more complexity to the driver. So yeah. Any question related to the unified memory? Okay, let's continue talk about streams. Streams in CUDA is a sequence of operations that execute on the device in the order they are issued by the host code. Stream is an important concept. So it's a method. It's a way for you to organize a sequence of operations which have the which have dependencies on each other. That means the first operation must finish before the second operation can happen. But those dependencies prevent us from running all these operations concurrently. But there are other operations that can be run at the same time. So for example, if you have two kernels, one is vector add, one is matrix multiplication. They operate on totally different data set. There's no restriction that you couldn't run them at the same time. So that's where the concept stream come from. So the first kernel is the vector add. So it's data transfer, kernel execution, and the transfer data back. Those three operations are in the one stream because they have the order. They must be happening in order. While another stream is the matrix multiplication. Still the same. Still the three operations. But those two streams, like here, the operations from different streams can be interleaved. So we can somehow, the hardware can manage those operations and make them progress concurrently in the different stream. Here, this is how the stream, how you create a stream, define a stream, could a stream create, and that's for the device data and the host data. So the for the kernel call, this is the fourth argument you pass. And for the CUDA copy, there's another. You have to add another argument behind the direction. So one more thing is here you have to use when you use the stream, so pass the stream as a argument of a CUDA copy, you have to use this function, this API. A synchronized host device mem copy returns control immediately to CPU. As we mentioned before, the regular CUDA copy, it's synchronized. So that means it won't continue the next CUDA call until the main copy is finished. Mm, so and those CUDA main copy async also require you use the host also require you use the pinned host memory. So that means for the host data you have to allocate with CUDA malloc host. So here the important thing is you start to think of asynchronous. So everything, so things are not blocking. So like if you launch so before we know that the kernel call is asynchronous. So when the CPU launch a kernel call, it won't wait for the until it won't wait for the kernel to become to be finished. It will continue doing its own work on the CPU. But we will see those asynchronous in more cases. So, but we at some point we have to do the synchronization. The host didn't. For now, we said the host didn't wait for any of the operation to be finished. Um, but we in some cases we need the host to wait until the data it need come back from GPU. So the CUDA API provides us several functions to do the synchronization. Let's start from like the stream synchronize, which means the host will wait for one certain stream is empty with all of the operations in that stream got complicated complete got complete. Also, the host can wait for event is get recorded. Mm, this one is very similar to CUDA device synchronize. I think we mentioned that CUDA device synchronized for the event. So for CUDA device synchronized means the host will wait until all the device all the thread come to a certain point. But for this is is also wait for the device, but those are for what for the CUDA calls uh, that is issued from only one CPU threads, not all the CUDA calls on the device. If we have multiple streams, how many different ways exist to do a complete kernel operation? So the straightforward way we have seen before is using just one stream is serial. It's called serial. We just do the three operations in one stream. But we can have a different way. So think of the vector add, for example. The vector, the I mean the element addition is totally independent with each other. So one way we can think of is we can split the data into two halves. So first we transfer half of the data to the GPU. Next, we start start the kernel execution for the first half. Then we copy the data back, and then we do the same thing for the second half. This is a way of doing it when we break up our problem. So at least this gives us the way of how to do things concurrently. But as what I said is, maybe I can draw. So is do this. This is a host to device, and then do a kernel. Okay. Then do this the device to host. For the second half, we do the same thing. Device host to device. In this case, you can see there's actually no concurrency. So what if as long as there is hardware resources like the bandwidth, once we finish the first man copy host to device, we can start doing this one. This one just as parallel with this kernel. That is shown in this figure. So instead of split into two parts, you can like split into here like 4 parts. But this you will see later. We have some assumption here. So this figure show more exist ways you can do them. You can pipeline different applications into different streams. Here, so in this figure, so those are in stream 1, those 3 are in the stream 2 because this need dependency. So we can think one operation in stream 1, like kernel execution, can be executed at the same time with another operation in a different stream. So you can see those are in different stream. This is stream, different stream. So in the two-way concurrency, we still get our host to device copy operation together, but we can split that into pipeline as well. So in this case, at this point, you have 3 different operations at the same time. So you can get up to 3x speed up. So instead of thinking how to add more stream on the GPU side, which is limited by the hardware resources, you can think of start using the CPU to compute. That's why we have this red layer. Uh, so, oh, another thing is, so you have to be aware that the the execution time, the time take to do the execution should similar to the time you do the data transfer, which is not applied to the vector add. When we do the vector add, the execution time is very it's it's smaller than the data transfer time. So this only useful to the applications which whose execution time is close to the data transfer time. This is the profiling results of what we have shown. This block are the are the work that is actually done. So if we only use CPU, we get 43 gig floating point operations, which is the throughput of the computation. Mm, but for the once we start to use the GPU, just using this serial means just using one default stream, uh, we will get this. So if you look at this figure, we can probably have a feeling that we get a 4x speed up. So if there's no stream, we have to add all of those blocks concatenated together. So if we start using CPU as another level of parallelism, we get more speed up. So still the same question I mentioned before, we need to think of our assumption. So until now, we see those parallelism. We have assumption, at least we have assumption that, or we can see this figure. The we have assumption is that the kernel execution and the data transferring can happen at the same time. So in the CUDA's terminology is we have a kernel engine and a copy engine. So we need to take into account how many copy engines are available. So let's take a look at one example, which is implemented in two methods. The first method is this is the number of streams. For each stream, we have a sequence of operations. First, we do the man copy, then we launch the kernel, then we do the man copy the data back. Then those sequence of operation will be repeated in order. It will be launched in order to different streams. Yeah, as I said, yeah, you do first to the stream one, the copy launch kernel copy, then the second you do in this way. The second method is you can see there are three for loops. The first one copy all the do all the host to device copy for all the streams, then do all the kernel launch for all the streams, etc. So do all the host to device, do all the kernel launch, do all the device to host. So the interesting result we can get from this this analysis. So sequential version is as I draw before. Since yeah, there's one kernel, but we can split the kernel into three stages and into four stages. Mm, this is the first version. Do uh do the first part in one stream. This is stream one, stream two, three, four. Um, but you can see this version. There's no improvement. There's no performance improvement. The reason is here. The here the host to device mem copy in the stream 2 could now couldn't happen until this one got finished. So they are in the different streams, but there's one restriction is there's only one copy engine. And from so how the copy engine execute the different operations, it is executed in order. Since in the for loop, this happened, this orange one happened before the yellow one. So this one, the in the stream 2 has to wait until the device to host happen finish. But in the second scenario, we have a different organization of when we launch those operations. I remember we launched the hosted to device at the first together. So yeah, so in this case, when when the copy engine finished the first hosted to device, the next scheduled into its engine is directly the host to device in the stream 2. That's why in this case we have at least 1/3 performance improvement. What we have talked about is for the device under 3.5. See here. Mm, so what we have seen, that's for the device which only has one copy engine. Uh, but in this case, now we have two copy engines. One we can use for host to device, one is for device to host. Mm, we can understand this case easily. The same thing here. Uh, here, the host to device man copy in the stream 2 can happen directly after the one in the stream 1. Mm, but the interesting thing is in the second version. uh, in the second version, the problem is we have less performance improvement. It is related to its ability to concurrently run multiple kernels. Mm, so recall the for loop. There are three for loops. The second for loop is it launch four kernels to four streams. So when multiple kernels are issued back to back to different streams, the scheduler tries to enable concurrent execution of these kernels. Mm, but there's only one kernel engine, so no way to concurrently run those kernels. So as a result, it delays the signal that normally occur after each kernel completion. So that's why they wait until the last executed kernel finish. Then it sends the signal to do the mem copy. Actually, this won't happen now. Let's see. That's only happen. Here. Yeah, it said until all the kernel finish. If the kernels are issued back to back in different streams. But this problem is only happens for the device with the compute compatibility smaller than 3. So here, so when the compute compatibility is larger than 3.5, I think that is Kepler. We won't have those problem. So this engine can, so in this case, the two, no matter which way you write your code, you will end up getting the same improvements performance.
What is that compute capability number?
It's a device property. So in CUDA, there's a API call called the device query. You can query the device, so you can use different device. So it will give you one of the property of that device's compatibility. This property is important one. Yeah. So if you start programming one device, you can first do the device query to get the different, like the property of the device includes many parameters, like the one we talked the maximal threads per block, the max number blocks SM can run at the same time. Yeah, at the same time. Those numbers are related to the compute compatibility. But but so you can have different devices with different names, serials, but they are still in the same compute compatibility. So that's why I said it's important because those parameters is correlated with this number. But there are other parameters that is individual device dependent. Mm, Uh, this is another example try to showing how we can overlap the execution with the data copy. I think this one tried to illustrate the default stream. Mm. Here in a for loop, we launch kernels to different streams, but after we launch to the stream I, we launch another dummy kernel to default stream. If there's no force argument, uh, that means you launch it to the default stream. Yeah, that's without specifying a stream. Uh, the runtime use the default stream. Mm, so there's something special with the default stream. It is implicitly synchronized with all other streams on the device. Mm, so you will see in the next figure why I said it will synchronize with all the other operations in other in it will synchronize with operations in other kernels. So in order to launch this kernel, you can this is the dummy kernel. Um, so you so once so the synchronize means it could not happen at the same time when other streams are executing kernels. So it will see synchronize. Yeah, it will. So so in the stream 13, it finished the kernel, but but in order to run this dummy kernel in the default stream, it blocks the next stream. So the operation in the default stream is synchronized means it must finish before the next operation other stream can start. So this is a bad thing. So it's like you serialize all the kernels. But there's one way you can solve this thing. Uh, so the CUDA 7 introduced a new option to use an independent default stream for every host thread. So you can pass this option. Um, so um, so in this case, the dummy kernel will be executed in stream 14. Uh, so it won't be executed in the default stream if you set the default stream flag. as per thread. Uh, so now we come to the last topic of our lecture. Is dynamic parallelism. Mm, so it's better to see this. Mm, sorry. We have seen before is only the CPU can launch the kernel to make sure to make a GPU work. But now we can do, there's another feature called the dynamic parallelism. We can make the GPU uh, generate work for itself. Uh, so it starts from the Kepler architecture. So before we don't have this feature. So the typical use case is used for dynamic load balancing, data dependent execution, recursion, and the library calls. These do not make much sense for now, but as you advance, as you see more CUDA code or to solve more complex problem, you will understand those cases. This is an example for the fluid simulation, turbulence simulation mode. Um, so here the you can see the fixed grid. This is initial grid, and so you can this and this one are fixed grid. So the grid means um, uh, I think this block, this checks are similar to what we programmed the CUDA block, which means the fixed number of threads in each block. The each thread in those block will uh, process certain pixels. Mm, but you can see a bunch of dark area here. These are do not have particles. I think in this case it's for particles. There's no particles at all, so it would make sense to have only small set of threads calculating this area. So the small set of threads means we have a coarse grid. Mm, but as we advance on the x axis, we can see the figure are you can see there are more particles you have to simulate. Mm, we need like this fine grade grid in order to have more threads working on the particles. Mm, mm. So if you call directly from host, you want to get a clear simulation in all the areas, you must launch this fine grid. You have to launch lots of threads. But that is not efficient. Like here, those threads are idle. So when when we use the dynamic parallelism is as we advance on the x-axis, we actually launch more threads. So we progress from further. We actually become more and more fine grid. This is one example how the dynamic parallelism is used. This is another. example. So in this case, the normal case is CPU launch kernel. The kernel gets executed on the GPU, then copy the data back to CPU. Maybe it's uh, um, some data that that needs to be progressed, that need to be processed into another places, like uh, some some information. Then it is sent to different advertisement website. So that means they are go back to the GPU to do more to do other operations. Mm, so this will come back and forth. So the CPU will involve several times. But with the dynamic parallelism, mm, so everything can happen only on the GPU as long as the CPU doesn't need any information the GPU computes. Mm, this is another case. The CPU, in this code, the CPU launched three kernels, uh, and A and B and C. So the kernel B, this is the kernel B. Inside kernel B, it launches another three kernels. Mm. So the coding style is the same as before. So that means this syntax can happen inside another kernel implementation. Still uh, the dimension of the grid of the block, the shared memory size, and the string. Here is the example for the LU decomposition uh, for both Fermi and Kepler architecture. As I said, the start from Kepler architecture, we have the dynamic parallelism. So before we have to do the kernel launch and then come back to the CPU, do some data management, do some work, and then launch the kernel again. Mm. But now you don't need to go back to the CPU. I think this example is normally happen when you call a GPU library. There is also a problem for how to synchronize the new launched kernel. Mm, uh, one thread, in this case, one thread launch a kernel may be based on if condition, since others are progress its own data. So there is some kind of synchronization that is happen. Uh, so CUDA provide you like the API synchronize functions to make this thread wait here until its children complete its execution. Mm, Also for the memory model, the child see parent state at the launch. The parent so here is important concept is the local and shared memory are private. So you allocate the local and shared memory to the parent kernel. Those areas are not shared by the children. So So those are private to the kernel call. Um, so for the child kernel call, it may allocate other resources. Um, Before CUDA 6, you have a limit how deep you can go with this dynamic parallelism. But now you have this variable called pool size. Pool size is default 2048. So you do not have limit, so you can do whatever you do. Also for concurrency, um, so um, this is the parent thread. So in one block, you happen to have several threads calling another kernel. On the left side, this is our default streams. So those kernels those kernel execution is serialized because the default stream, as I said, is synchronized. It's synchronized. It means uh, all the operations has to be executed in order. Mm. But in order to do them concurrently, you can launch them. This thread can thread 0 launch to stream 0, then stream 1. Mm. In For another block, thread 0 can launch into another stream. So this stream 0 is different from this stream 0. Mm, Now we are showing an interesting example called the level set algorithm. We basically said, oh, I would like to involve the area, um, but I have to stop involving until stop involving the area where pixel intensity or color intensity changes. Here, like you keep involving until you see white pixel. Um, so you spawn a lot of threads, and you look at the neighboring pixels. If there's no white pixel around it, then mark it and keep expanding. Mm, mm, so in this case, is you decide the number of threads will be launched neighboring for the neighboring for the neighboring pixels. Mm, One application of this algorithm is like a tumor detection. We can see that later. Mm, this is the involve. I think this is the kernel. But what should I see here? there are three kernel calls, not three. So there's a loop. So the uh, LSS means level set as step. This is step one, step two, and step three. So the step two get executed multiple times. I'm not sure what is really in how these are implemented, but you can get an idea how the number of threads you launch across different pixels are get changed. Another example is a recursive, how we do recursive on CPU, GPU, and GPU with dynamic parallelism. We will use the Fibonacci series, for example. That's for CPU. It's just recursion, calling this function again. Uh, this is the kernel for GPU implementation without dynamic parallelism. This is with the dynamic parallelism. This is probably not a good implementation with dynamic parallelism because inside the kernel it launches another kernel but only with the thread number, only with one thread. But as we said, we repeated several times, there are 32 threads at this execute at the same time in a warp. So if you only launch one thread, there are 31 threads idle. This can be proven when we see this result. Um, there are three bars, but you can only see one, which is the Fibonacci on the GPU side with dynamic parallelism. This is the runtime. This is execution time. Uh, as we increase the number of as we increase the number to calculate, actually have much we have worse performance. But for the CPU and the GPU without dynamic parallelism, you couldn't see them. They run so fast. The 0 is for the CPU implementation. The 30 or 40 is for GPU without dynamic parallelism. Mm. So as soon as we start scheduling more kernels, yes, as we go with larger number, we have to scheduling more kernels. This, but those kernels are not fully utilized hardware. So 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 that's why we get those worse performance. So the takeaway of this is do not overdo dynamic parallelism. So it's not suitable for the recursive algorithm. This is the summarize about the fact when we should use the dynamic parallelism. So um, so the general recommendation is when the child grid with a large number of thread blocks, you should use it. But if you only have a child launch a small number of threads, it's not a good implementation. or the thread blocks with large with hundreds of threads. Mm, mm. And also look at the nested parallelism for tree processing. So when you should think of dynamic parallelism as a tool when you are facing certain problems like a graph problem, the tree. So you will use this like nodes has relationship with their neighboring nodes or the pixel. In that case, you should think of choosing the dynamic parallelism. Mm, I think that's the end of today's lecture. Tomorrow we will do our last lab. Mm, thank you. Any questions so far?